Hello, my name is Yi Sung. I am the application engineer for digital power products with linear technology. Today, I'm going to talk about a very exciting new product, LTC3880, a dual-output synchronous standalone controller with digital power system management. Digital power has been promoted by many companies for several years. However, digital power has different meanings to different people. Some consider the digital power to be comprised of digital management functions and a communication link with the power supply. Others say that digital power is a digital state machine with digital pulse width modulation. Regardless of the definition, when digital power is done correctly, it can reduce power consumption, reduce time to market, exhibit excellent stability and transient response, and increase the overall system's reliability. The LTC3880 is a product that can meet all these requirements. The LTC3880 uses a fast analog current mode architecture with a digital power management interface. It can regulate two independent outputs or be configured for two-phase single output. An onboard differential amplifier provides the true remote output voltage sensing. Integrated gate drivers can power all N-channel power MOSFETs from the input voltage ranging from 4.5 volts to 24 volts. And it can produce 0.5% accurate output voltage up to 5.0 volts with output current up to 30 amp per phase. The LTC3880 can do inductor DCR current sensing to save power loss and cost. It can also provide the temperature compensation for the DCR variations over the temperature range. This shows the control loop structure of LTC3880. The LTC3880 has a well-understood analog current mode control loop to guarantee the optimum loop stability and the transient response, which sets it apart from the other digital controller in the market. The pickup mode control structure also ensures cycle-by-cycle current protection as well as accurate and fast DC and dynamic current sharing. This shows the control structure of a typical digital controller with digital voltage mode control. The digital feedback loop has a voltage analog to digital converter, digital compensators, and digital pulse width modulators. Therefore, the digital control will introduce the quantization and delay effects, which will lead to larger static voltage ripple and a slower transient response. A fast analog current loop provides superior performance, as shown in the transient response comparison of an analog control loop to a digital control loop. In this example, the LTC3880 reduced the bulk output capacitance by 50% in comparison to the digital control loop. The analog control loop also has better stability and shorter settling time. In addition, the digital control transient response experiences oscillation prior to settling due to the quantization effects and the limitation of its ADC resolution. In addition to its superior analog performance, the LTC3880 also provides comprehensive digital power management, support over 100 PM bus commands, and on-chip EEPROM. You can program output voltage, margining, current limits, input and output supervisory limits, power-up sequencing, tracking, and switching frequency. The on-chip precise data converters and EEPROM enable the capture and the non-volatile storage of regulator configuration settings and the telemetry variables, including input and output voltage and currents, duty cycle, temperature, and fault status. This table shows key parameters that can be programmed with the LTC3880, the telemetry readback capability, and the comparisons with alternative solutions. The LTC3880 has the best accuracy. The LTC3880 is supported by the LT PowerPlay software, an easy-to-use and powerful GUI. Now, let's design an LTC3880 power supply with LT PowerPlay. In this demo, I paralleled two LTC3880 standard demo boards. The application has 4 output rails. When we first launch LT PowerPlay on the computer, It maps out the entire bus and reads the hardware configuration into its displays. We can find 4 rails and show here. I can easily see the power-up sequencing configuration in the sequencing overview window. Now, the 4 rails will power up with coincident tracking. Let's use the oscilloscope screen to observe the startup waveforms. I will use the group on functions to turn on the supply. OK, the 4 rails are powered up as we expected. Now, let's change it. I want the 4 rails to start up with the same rise time, let's say 5 milliseconds. Type in 5 milliseconds to the T-on-rise register, then copy and paste to the other rails. Very simple. Write this to hardware and we will see that programmed sequence. Let's do the group operation again. Here we go. The 4 rails now are powered up with the same rise time. We can also program various fault configurations with the help of LT Power Play. Under the fault response subtab, we saw different types of programmable faults, like under voltage, over temperature, and over current. For example, we can set the output under voltage fault response to be infinity retry, which is known as hiccup mode. Now I short rail 1's output to ground. This action will lead to a UV fault. This channel will shut down and then do a retry with programming delay. When the short circuit condition is released, the rail will return to normal. In conclusion, the LTC3880 combines the best-in-class analog switching regulator controller with precise mixed signal data converters for unsurpassed ease of power system design and management, supported by the LT Power Play software and powerful and easy-to-use GUI. The LTC3880 has applications in computers, datacom, telecom equipment, and storage systems. For additional information, please visit www.linear.com. Thank you for watching.